Welcome to 6502 Assembly Language Programming. In this video, we'll look at performing 16-bit arithmetic on the 6502. To review, the carry flag is useful to propagate data when operating on 16 bytes of data or more. In this video, we'll use it to perform 16-bit addition. The algorithm is very simple. First, we'll clear the carry flag, then use add with carry to add the low order bytes. Since the carry flag is clear, it will not affect the result of that addition. After storing the result, from that, we'll use add with carry to add the high order bytes. If there is a carry from adding the low order bytes, it will be included in this addition. Finally, we'll store the result. When you're storing more than 8 bits, there is a question of what order they should be stored. For instance, you could store a 16-bit value in one of two ways, with the low order byte first or the high order byte first. Storing it with the low order byte first is called little endian. Storing it with a high order byte first is called big endian. In this video and throughout this course, we'll use the little endian convention. And later on you'll see how that makes sense in working with a 6502. This slide illustrates how data is stored using either convention. We're storing the hexadecimal number 1234 at address 80. With little endian, the $34 is stored in the lowest address, which is 80, and $12 is stored in the next address, which is 81. With big endian, they are stored in the opposite order. So let's go to the 8 bits and 1 byte IDE and code our algorithm. Now, if you saved your work from a previous exercise, you can start at this link, which ends with playatari.html. And note the A has to be capitalized, sorry. If you haven't saved any work yet, then go to this link, which ends with course_DASM.html. Okay, we'll see you there. Here we are at the 8 bits and 1 byte website, where the website has loaded up the work that we saved previously. We're interested in exercise 2, which is stored in the ex2.asm file. Here it spells out our task. Add the 16-bit value in the variable inward_0 to the value in in_word_1, putting the result in out_word. So let's just go ahead and code that. The first thing I'm going to do is clear the carry flag. Move the mouse out of the way. Then we'll load up our first parameter from in_word_0, load low order byte input. Well, that gets spelled. We're going to add that to the contents of in_word_1. Add to contents. Or I should say add to low order byte. The second input I change this to first input. Okay, now since the carry flag is 0 by virtue of the CLC instruction, it would not have added anything to this operation here, the add with carry. That's what we want. We're going to store this result in out_word. Store low order byte of result. Now we're going to load in_word 0 plus 1. Load high order byte of first input. Then we're going to add with carry to in_word_1 plus 1. Add high order byte of second input. Note that this result will be affected by the carry flag. If we had a carry coming out of the first add with carry operation, that data will be included in this add with carry. Okay, so let's store the result of that in out_word plus 1. Store high order byte of result. So now we're going to change this LDX, and you may recall from previous videos that the X register tells the main code whether or not this exercise has been implemented. So now we're making the claim that it's been implemented. Please check our result. Let's run it. Let's go to the output screen first of all, and you can see that we have a green light. We have 3 green lights, so we got that right. Yay for us. So we've solved the exercise, but I want to take a moment to review the contents of the screen when you select the Run tab. The first element is the listing. This is produced by the assembler, and it is a document that shows you what is where in memory. So here, for instance, on the left-hand side of the screen, we have these numbers starting with F. Those are addresses. And so if the assembler has generated some code, like this 18 is the CLC instruction, that is at address F014. So that's the address column. The next column over is the code. If it's generated any code for a line, it'll be here. And then moving over one, if there's a label associated with the line, here my mouse is pointed at EX2. That's the label for this subroutine directive. That's the column you'll find that. And then further over, you find the instructions and the directives. Now, all the variables that we're using right now are base page instructions. So for instance, if you look at this variable load A in_word 0, you can see the address is hexadecimal 84. And you can find these by in memory by clicking on the log display, scrolling down to the bottom of it, and then finding the address here. So we're looking for address 84. This display is organized, this memory display here that my mouse is on, is organized into columns. Each column is groups of 4 bytes, which are displayed as 8 characters. So this is address 80, this is address 84, 88, and 8C. So by using the listing and the memory display on the log tab, you can find your variables to see what's in them. Once they're loaded into a register, for instance after this LDA happens, you can look at the CPU tab to see what's in the register. And again, you can change the base that's being displayed, binary, decimal, hexadecimal, to suit what you need at the time. Okay, well, that concludes this video. I hope you found it of some value and I hope you enjoyed it. Thanks very much for watching. As always, it helps me if you can like and subscribe. Have a great day.